we do. Maybe the first technical difficulty is, oh, there we go. All right, so I'm going to start, assuming there are many of you that haven't really followed the mission or been too involved. I wanted to give you a little primer on OSIRIS-REx and kind of what the goals were before we even launched and why we picked this particular asteroid. And I wanted to focus a little bit on the OSIRIS-REx Laser Altimeter, both what it is and a little bit maybe of the story of how it came to be. In terms of its contribution and what actually happened in the mission, we'll focus again on OLA, which is Canadian instrument, and a little bit of the story, not just the end result of what we have accomplished, but kind of the ups and downs along the way, and a little bit how it appeared to me as it was happening. And then we'll talk a little bit about the TAG, which was the sample collection that happened very recently. Sorry, I'm going the wrong way here. All right, so what's OSIRIS-REx? So like every other space project, OSIRIS-REx is an acronym. In this case, it stands for the goals of the mission. So we have origins, and I'll expand a little bit on all of these, but these kinds of asteroids are sort of little laboratories of the early solar system, so they can inform a lot about the materials that made up Earth in terms of water and organics. A lot of what we know about the broader asteroid population, we need to understand better, so we can look from the Earth and better identify things, the particular classes of asteroids that are there. So that's spectral interpretation. Asteroids are interesting from a resource point of view. They're interesting from a security point of view because we're really the first generation that could protect ourselves from a potential collision. And then we want to explore the regolith and actually bring a bit of the sample back to our labs here on Earth. So science goals, just said another way, or the goals we had that would actually inform back to those top level goals in the acronym. The first one, the most important one, and why the sample collection of a couple of weeks ago was so important, is to return and analyze a sample of Bennu. We also want to create maps of the asteroid, document the sample site, because we actually want to understand the context for that sample that's being returned. And then the comparative telescope-based observations, that's about understanding Bennu so well and how it looks from remote sensing, so that we can better understand similar asteroids that we don't have the luxury of sending a spacecraft to. And then we'll get back into measure the orbit deviations, but this has to do with the security goal and some of the interesting physics that happens on these small bodies and why they're difficult to keep track of. So in terms of our timeline, so we launched in September of 2016. The goal was to study Bennu for up to 505 days. So this is all the pre-goals. And we, in particular for OLA, the important phase was mapping the surface of the asteroid from a distance of as low as 700 meters. And then the goal, a successful sample collection would be just 60 grams of regolith. And 60 grams doesn't sound like a lot, but 60 grams is really enough to put most of it away for the future and unplanned analysis types, but still to meet all of the analysis goals that we had planned as the mission concept was being formed. And that sample should come back to Earth in September of 2023. Then curation of the US sample is at Johnson Space Center, just like the lunar samples, and they will be distributed there. Now Canada gets 4% of that sample for our contribution to this mission. So we have an activity plan to figure out what we're going to do with that 4% and how we're going to safeguard it and curate our own bit for the future Canadian scientists. So here's a cartoon of the spacecraft. I'll show you some real pictures later, but we're talking about approximately 2 meters on each side with 8.5 square meters of solar array course, it's a solar-powered mission, so we've got batteries. And then the sample return capsule, which you actually can't see in this picture, but I'll show you later. But it has previous mission heritage from a mission called Stardust. Okay, so in terms of each of those goals, and a little bit talking about the hardware that was on the spacecraft, is on the spacecraft to accomplish these. Return and analyze a sample. This is the major goal. If we did nothing else, we wanted to do this one. So 60 grams of material, as I said, and it uses the touch and go sampler. So we've been very careful during this mission not to talk about landing on an asteroid, because when people think about landing, they think about, you know, the 7 minutes of terror landing on Mars. And this is not really like that. It's much more akin to a spacecraft docking maneuver. Everything happens very slowly, although there was still a little bit of terror involved. So touch and go is what we called it, and, you know, TAG for short. So here's how the sampling mechanism works. It's kind of a pie plate, thick pie plate kind of thing. And you can think about it as a reverse vacuum cleaner. You know, I often have gotten children ask questions about, why can't you just suck it up? And well, there's no air to suck it up with. So we've actually had to bring our own, and we blew the air down into the regolith and directed material up into a capture mechanism. So we're really just talking about a few seconds. The challenge with this, so this was a bit of a trade-off, this kind of sampling mechanism. So if any of you have followed the Japanese mission, they used a very different concept, and so they maybe had less constraints about how they actually, or the condition of the asteroid and where they selected their sample site to be. However, they also bring back a very small amount of material compared to what we could bring back with this one if everything goes well. But for everything to go well, we really needed sort of asteroid materials that were sort of at the, you know, 2-3 centimeters and below. So that's been a big part of the challenge in selecting a sampling site. So here's some actual pictures from a poster produced by the mission. So you can see how TAGSAM sits on the arm. You can see gas canisters on the arm. You can see where it sits on the spacecraft, and you get an idea of the size by the two pictures with the person involved, and I know that person. All right, so here's, so I'm going to struggle maybe with this video. Told you it was a new one here. All right, we can skip that, and I'm going to show you the real stuff a little bit later. Hopefully the other videos work, or we'll have to regroup at the end. All right, so in terms of creating maps of the asteroid, this was really for a number of goals, but we wanted to map the global properties, the chemistry, and the mineralogy of this really primitive asteroid. In order to do that, we wanted to create spectral maps to understand the mineralogy and some of the thermal properties, image maps, elemental maps. So this was an interesting student contribution. And then topographic maps, which we did 2 ways with camera-based approaches that I was also a bit involved in, and then the LiDAR-based modeling from the Canadian instrument. So all these are covered by instruments on the payload. And so it was really, you know, one of the reasons to go to an object like this and grab a sample is, instead of finding a meteorite that's, you know, not so pristine because it sat around in the Earth's environment and it's entered the Earth's atmosphere, we can actually go and say, okay, this didn't just come from this family of asteroids, we think came from this particular asteroid. Not only that, it came from this particular place on this asteroid, and we have really good geological context on the asteroid to understand where the sample came from. So that's very unique about a sample return. mission. Okay, so here's a model of the spacecraft with really all of the instruments. So we had a camera suite, so that's the OSIRIS-REx camera suite, or OCAMs. This is really a combination of 3 cameras that we'll talk about in a little more detail. We have the OSIRIS-REx Laser Altimeter, so this is the instrument I'm responsible for, both in concept and then responsible for the science data and the science observation plan that's associated with the mission. And so that was paid for by the Canadian Space Agency, and it was designed and constructed by McDonald, Detweiler and Associates, MDA, and Optech, Teledyne Optech, both in the Toronto area. Then there were 2 spectrometers, a thermal emission spectrometer. So this is a long wavelength spectrometer, OTES, OSIRIS-REx Thermal Emission Spectrometer, and OVIRS, which is a shorter wave, so from say 400 nanometers through the visible into the near infrared, out to about 3.5 microns, I think, or so. And then REXIS, which is a X-ray spectrometer, which was not one of the main instruments on the mission, but it was actually a student project by MIT and Harvard. So you can see where they're all situated on one side of the spacecraft. That large circular object that's closest to the bottom, that's actually the communications antenna. The smaller circular object on the center near the instruments, that's the sample return capsule. And then the instruments are around it with OLA way over on one side, because we actually used quite a bit of energy, and so we tended to heat up the deck. So we were better placed away from those other cameras. So here's some examples of real hardware. So again, here's the spectral map. So OVIRS from 0.4 to 4.3, I think as built, maybe closer to 3.5. And then I think OTES actually extended out a little bit beyond 50 microns. They used 2 different spectrometer technologies. Here's OVIRS. So this was built at the NASA Goddard Space Flight Center, and its major focus was mineralogy and location of organic compounds. And its technology really used a series of, used a 2-dimensional imager and a series of linear filters that then were constructed into a spectrum. OTES, built by Arizona State University in Phoenix. And this was mineral, but also thermal maps. So, you know, one of the big questions we had on this asteroid from a sampling perspective is, you know, where would we get this regolith, this 2 centimeter and smaller particulate matter? So, you know, obviously we had images to help choose, and we had topography, which we could infer, you know, where finds may have fallen. But here we actually have the ability to look and see how the surface heats and cools. And that also gives us some information on the particulate sizes and the amount of void space in the near regolith, which is another piece of evidence that supported the tag site collection. Tag site. And then here's the 3 cameras. So Polycam, an 8-inch telescope. That's where we got our first images of OSIRIS-REx when it just looked like a spot, single pixel. But it was also used with some different focusing right up close to the asteroid and gave us our finest resolution images of the sample site. And then MapCam is kind of that intermediate range, and it produced color images of the asteroid while we were in orbit. And then SAMCAM was all about imaging during the tag collection, and then looking also at the sampling device to assess how much sample we got. All right, so I think just some other pictures of the hardware. So a little more detail on MapCam. So as I said, color mapping. We use this not just for on orbit, but we also used it for looking for plumes. So one of the big questions we had, were we actually going to see this asteroid off-gassing and sending plumes? That had, you know, enormous science implications, but also had implications for the sampling and the safety of the spacecraft. I'm not going to dwell too much on this. This is what SAMCAM looked like. Okay, and here's the student project, REXUS. So I personally have yet to dig into the data on this, so I won't be able to answer too many questions on how we finally did, but it was fun interacting with the students that were operating there right alongside us, doing their instrument planning for operations as we were doing the instrument planning for the other instruments. And a little bit more on the hardware here. Okay, and here's OLA. So OLA was essentially two electronic boxes with these electrical umbilicals between them. The box on the left was really about power conversion, and it had the computer in it that dealt with the command and control. And then on the right was really the business end of OLA. So you can see the window. I'll show you some details of inside, but there's a 2-axis scanning mirror in there, so we could actually point our measurement spot very, very accurately and very, very quickly to where we want it on the asteroid. We can talk a little bit more about the importance of that. And then we had 2 different lasers on there, one that was operational from out beyond 7 kilometers from the asteroid, and then the other one came in when we were up to about 1 kilometer away from the asteroid. So some pictures here of OLA. In the top left of this poster, you can see OLA in the thermal vacuum test facility in the basement of the building where my office is in at York University. So it was nice to see that tested so close by. I didn't have to go very far for that one. All right, so still on a little bit on the science goals here. So we wanted to document the sampling site. As I said, it really required some very fine mapping because we were focused on this, you know, couple of centimeter to finer particles. So we were all the instruments were really required to operate down to as low as 200 kilometers from the surface of the asteroid. So that's very, very close for a remote space mission to fly to an asteroid without touching it. And the interesting thing is we planned for a 25-meter radius error ellipse. So that means this tag, the actual touching of the asteroid where we were going to sample, we were planning that we could have 25 meters of uncertainty associated with exactly where we touched the asteroid. And we thought we would be able to find a nice smooth area like that on the asteroid. And Bennu had some different ideas. Okay, so this is an interesting one. So this is about the security part of OSIRIS-REx, so measuring the orbit deviations. So there's a couple of interesting effects. One's called YARKOVSKY effect, which is the main one we'll talk about here, and a related effect called YORP, which has to do with the asteroid spin rate changing, that have to do with how the asteroid heats and cools from the sun. So if you have a rotating asteroid, and I think I have another picture to explain it a little bit more, but these small forces can move the asteroid around, and we're talking about really small. Like I think one of my colleagues used the analogy of maybe, you know, 3 grapes on your hand of force that operates 24/7. But to understand these, you really have to have a very good thermo-optical model and physical model of the asteroid, and that's difficult. So this means that when we want to put collision probabilities, you know, risks of impact with Earth, you probably heard about them on some of the news where it's, oh, we have this much probability of an impact over the next, well, for OSIRIS-REx, we often talk about over the next couple hundred years, and you think, oh, well, you know, aren't orbits very easy to predict, and don't we understand them fairly well? And the answer is yes, but these small forces really, over long periods of time, make a big difference. So we wanted to understand those better. So here's what I mean about the Yarkovsky effect. So as the asteroid rotates, one side heats. As it goes into its night, it's obviously hotter just as it enters its night. And just before dawn, it's obviously much cooler than it was just as it began it, that portion of the asteroid began its night. So there's a differential amount of photons that are let off in one direction versus the other. And if you have a prograde rotation, you actually move the asteroid further out in its orbit and retrograde in close. And so OSIRIS-REx, because we were spending so much time in close proximity, and we had excellent ways to measure both where the spacecraft was with respect to the Earth and therefore the Sun, and we had excellent ways to measure the distance to the asteroid from the spacecraft. It was, and all of these great thermophysical models, we had a very good opportunity to make sure we understood this effect, and we're still writing some papers that should come out over the next 6 months or so to prove out these models. So one way you can see it's important is most of the asteroids, I think everyone here would know, are in the asteroid belt, but there are these gaps in the asteroid belt. And these are really resonances with the major planets that actually can act like a little bit like pushing a swing, and you give it a little push, and if you do it at the right times, the person on the swing set swings further and further. These can be mechanisms for asteroids to move out of the asteroid belt and really enter into collision probabilities with the Earth. And one of the forces that can move you around in the asteroid belt and move you into one of these resonances is this Yarkovsky effect. So it can be very, very important. Okay, and maybe I won't talk too much about the telescope-based operations. So Bennu is what we call an Apollo asteroid. So it spends most of its time between Earth and Mars, but Bennu does cross the Earth's orbit. So it is, when we chose the mission and we chose Bennu, it was the one that had the highest collision probability over a couple hundred years that we knew about. I think it's now second. I think it's still second, but it might be third. So it is one of the ones we wanted to keep track of. The other way we keep track or classify asteroids is based on their spectral signatures. So these little squiggles are meant to be spectra, and so depending on little features of these optical spectra that we usually have from ground-based telescopes, we classify our asteroids into different categories. And if we've done it right, you know, those categories are meaningful from a mineralogy or other point of view. All right, I'm a little, oh, here we go. So here's just this is the video that was all about OSIRIS-REx before we sent it out. Can everyone hear? Hey, is this, can everyone hear Randy, can people hear the video or not?
If you can hear it, we can hear it.
Were you hearing it there?
No, we can't
There it
hear
is. It came and went.
Okay, I shut it down. I just wanted to make sure everyone could hear it. Okay, perfect.
Okay, we don't hear it. Are you hearing it in your earphone? Michael? Do you hear it? Because we do not.
Sorry, are you saying you can't hear it?
That is correct.
All right, see, this Zoom thing for something like this is,
Can you make it audible to your microphone?
yeah, probably. Just a minute.
Okay.
I'll come off my headset for a minute then.
Yeah.
All right, we'll give this a go then. I'll try it for just a second and then you can tell me if you can hear it.
All right.
Can you hear that now?
Yes, maybe turn down the volume a little bit.
Okay.
But yes, definitely heard that.
All right, perfect.
All right, thank you.
If you want to study a piece of the early solar system in a lab on Earth, what do? To better understand the evolution of our solar system, NASA is sending the Origins Spectral Interpretation Resource Identification Security Regolith Explorer, or OSIRIS-REx, to study a near-Earth asteroid called Bennu. OSIRIS-REx will launch in 2016 and arrive at Bennu in 2018, where it will spend over a year surveying the asteroid in unprecedented detail, determining its chemical makeup, mineralogy, and geologic history. The OSIRIS-REx payload contains several instruments for remote sensing observations, including high-resolution cameras, LiDAR, and X-ray, visible light, and infrared spectrometers. Knowing the physical properties of Bennu will help scientists to refine its orbit over time, including deviations caused by heating and cooling from sunlight, and it will allow them to pick a site for OSIRIS-REx's primary mission, retrieving a sample of the asteroid for study on Earth. In 2019, OSIRIS-REx will deploy its touch-and-go sample acquisition mechanism, or TAGSAM, and slowly approach the sample causing loose rocks and soil to flow into the collector. Since Bennu may be rich in organic material or water left over from the formation of the solar system, sampling it could reveal whether the building blocks of life were present at that time, perhaps providing clues to the origins of life itself. After moving away from the surface, OSIRIS-REx will perform a spin maneuver to measure the mass of the sample. Then it will carefully stow the TAGSAM head inside the sample return capsule and prepare for the journey back to Earth. Upon arriving home in 2023, OSIRIS-REx will release the sample, giving us a piece of the ancient solar system that will be studied for decades to come. OSIRIS-REx is a joint project of the University of Arizona's Lunar and Planetary Laboratory, NASA's Goddard Space Flight Center in Greenbelt, Maryland, and Lockheed Martin Space Systems in Denver, Colorado. Dante Loretta is the mission.
All right, good enough. Sorry for that little technical difficulty in the middle where my headset decided to reconnect again. All right, so let's talk a little bit more about why Bennu. So what I just showed you was the plan. You know, that's what we had planned as we launched and before we actually got to Bennu. So let's just talk a little bit more about why Bennu. So here's what we knew about Bennu before. So we knew about its, you know, I showed you the little spectral line, so we knew how to classify Bennu. We knew it was going to be a dark carbonaceous asteroid. We thought the albedo was about 4%, so that's, you know, a very dark, like a big dark chunk of coal. We knew it spun at 4.3 hours. We knew its diameter was about 500 meters. We knew it had a bulge, equatorial bulge, you know, caused by the spin. And this was a radar model. A little bit sad, actually, this model, because this model was taken at the Arecibo Observatory, which I'm sure many of you know is actually going to close. So this is that big observatory made famous in the James Bond movie. Which one was it? GoldenEye, maybe? So a lot of people know about this, and it was really, it's going to be a irreplaceable astronomical asset. But we also had some ground-based understanding of the thermal properties of this asteroid. And thermal properties were quite compatible with there being large, smooth areas on the asteroid, which, you know, is part of the reason why we thought finding a 25-meter spot for spacecraft to touch would be easy. So how do we get to, someone's got their mic on, I think. So how do we get to selecting Bennu? Well, you know, there's more than 500,000 asteroids in the asteroid belt, but that's a long way to get to. So there's 7,000 of them that are closer to the Earth, and you know, that's sort of, it's easier to get to, and it also ticks a little more the security goal of OSIRIS-REx, because if they're not near the Earth, they're not really much of a threat to our security. And we have to think a little bit about getting to them and getting back. So of those 7,000, there's 192 that would seem to be easy to get a sample back from. And then of those 192, only 26 of them have diameters greater than 200 meters. Well, why is that important? If you have too small an asteroid, you there's not enough gravity to easily navigate around. So the gravity helps us a little bit around Bennu. Sorry, I'm just going to struggle with my voice maybe a little bit through the rest of this. So we did actually, you know, it's kind of a rough orbit, and the orbit is hard to maintain, but we did orbit around Bennu. Those of you that like the Guinness Book of World Records, I think we actually have a record in there now about the smallest orbit around any object. And that was only made possible because Bennu was large enough with enough gravity to orbit. Then only 5 are these carbon-rich ones, which are the origins part of OSIRIS-REx. And so out of those 5, we selected Bennu. So it doesn't take long to go from 500,000 down to just a few to think about. Okay, so let's talk about OLA. So a little more detail here. So might not talk about all of these too much, but OLA really had, say, 3 major goals. So, you know, one that we've talked mostly about would be mapping the asteroid very, very accurately. The other one is we actually supported spacecraft navigation. So because we actually could range to the surface and provide a very good number for that, a very accurate number, it helped the navigation team with their calculations to more quickly arrive at navigation solutions. And then there's this question of understanding our position very well for the Yarkovsky effect understanding. So how did we get to OLA? Well, before I was at York, I worked at MDA, and I was kind of responsible for starting the Phoenix instruments, which were Canada's first instruments that went to Mars. And one part of those instruments was an atmospheric LiDAR that actually shone lasers up into the atmosphere and actually measured dust and clouds in the atmosphere, and actually found it snowing on Mars for the first time. So one of my colleagues at York was the principal investigator for that instrument. So the key part of that was a laser, and then we also did for the US Air Force experimental satellite another instrument that actually had a 2-axis scanning mirror. Could someone shut their mic off, please? Thanks. Actually had a 2-axis scanning mirror that could point the laser around and measure not just a profile of dust and clouds, but actually get distance to a hard target. So when the same team that we did the Phoenix instruments called me up and said, what could we do for a mission to an asteroid? The answer was fusing these 2 things together, and that's really where OLA came from. Sorry, I'm losing my voice a little bit. All right, so here's what OLA looked like from an operations plan point of view. And actually, you know, we executed very similarly to this. So you know, I said that OLA had two different lasers. So one laser measured at a rate of 100 times per second, and that started out, you know, beyond 7 kilometers. And the other one had lower energy, so it couldn't range out to 7 kilometers. But its advantage was it measured 100 times faster than that at 10,000 times per second. But if you think about orbital ground track velocities around a small asteroid like this, they're not in the 7 kilometers per second range like they would be around Earth, but they're more like 20 centimeters per second. So if you actually had a LiDAR like OLA that couldn't point, you actually have a problem where you have a very, very fine track of measurements overlapping one another at 10,000 times per second, but you would never get global coverage of the asteroid. So we added this 2-axis scanning mirror so that we could very, very dexterously point our measurements where we wanted them in order to get the kind of coverage we needed in the fairly short times that we had. So we started out 7 kilometers away. In this case, was called the preliminary survey phase, and we used the mirror only to move back and forth in the spacecraft motion for the other axis. We planned on doing the same thing in what's called the detailed survey phase, and here we were only 5 kilometers away. And the way to think about this one is we were sitting over the equator of the asteroid, and we were nodding the spacecraft up and down, and OLA was pointing along back and forth along lines of latitude until the whole asteroid rotated around once, and we did that for multiple stations. Excuse me. And then we were not supposed to have any activity between detailed survey and what was called orbital phase B, but we did, and I'll talk to you a little bit more about that later on when I explain, you know, what actually happened and some of the ups and downs during the mission. And then in what's called the orbital phase B, this was really OLA's time to shine. It was a 5 or 6 week phase of the mission where we were in a near terminator orbit, so going over the poles, and the asteroid was rotating underneath us, and we took what was really 2-dimensional images of the asteroid, and were able to put them together in a global map. And then 500 meters down over the prospective sample sites, we were to collect the highest resolution imagery that we could. So that was the plan. I'm just going to skip over these a little bit because I'm talking too long. Here's a little bit what OLA looked like looking down through the, if you remember, the black box had a window in the top, and this gold mirror here is our 2-axis scanning mirror. And so that was right underneath the window. So the laser would both go out through that window from the center of this mirror, and the reflected light would come back in and be reflected off this what's labeled here as the receiver, and then into hit a avalanche photodiode with a very very good timing circuit, which would measure the time from the pulse going out to the pulse coming back, and use the speed of light to get the distance of that spot to the asteroid. And if you know where the spacecraft's pointing very accurately, you have you have some constraints on the asteroid's position and rotation, and you know where OLA's pointing very accurately. All those things together, you can put together a whole shape of the asteroid very, very accurately. So this was our ground-based calibration. So we had some walls with very accurate targets surveyed in, and this is an example of data we had where we actually could calibrate not just the range, but also the position of the mirror by knowing the exact relationship between these little bullseye targets that were surveyed into a wall. All right, so getting to Bennu, we'll flip through this fairly quickly, but here's some real hardware pictures, so it gives you an idea of the size of the spacecraft. And this was at the test facilities at Lockheed Martin near Denver as the spacecraft was getting integrated, and OLA was getting integrated onto the spacecraft to make sure we could talk and it would survive launch and all of those other good things. This was launched from the Cape in September 2016. So it was pretty cool. It's fairly significantly sized launch vehicle. So exciting. If you've never seen a launch, definitely get to one. And just too many things on a small screen here. All right, so here's a little bit how the journey from Earth to Bennu went. So we launched, heading towards Bennu. So we launched in September of 2016, and we got to proximity operations of Bennu in December of 2018. So we needed to use the Earth along the way here for a little bit of extra energy. So this is what's called a gravity assist. And we reached Bennu in December of 2018. Okay, so OLA'S first encounter with Bennu was this what's called preliminary survey. So here we were, nominally 7.5 kilometers from the surface of Bennu, and the plan was to do 3 passes over the North Pole, 1 pass over the equator, and 1 pass over the South Pole. And really our job here was to help navigation and to collect enough data so that we could put some scale to another method of getting a shape of Bennu, which was a camera-based one. But a lot of that shape is inferred, so having real measurements of the shape and the size from OLA was very important part of this phase. So what we expected was to get each of these passes, if you can see on each of these passes, right in, not along the center line, but just a little bit outside, there's some places labeled OLA, and those were each about 40-minute passes. We were measuring at 100 hertz. So all told, we were expected in this phase to get something like 500,000 measurements, if I remember my math properly. This is what we got from 1 pass. So instead of getting lots and lots of points, we got, I think there's on the order of 700 here or something like that. We got about, let's say, 1/4% in this phase of the data that we expected to get. So this is one of these places in this mission where you're both, hey, I got some points, so the instrument's working, but where are all the points I expected? And we actually haven't had a chance to go back and do some solid modeling, but some of the answer here is because Bennu was much rougher than expected. Some of the answer may be that we had a little bit of degradation in our laser from launch. I haven't really put percentages to each of those. So this is one of these, it was both a high and a low point because, hey, it works, after so many years and so much effort. So this was from 2008 when we started, and this was December of 2018. But certainly it was a little bit disappointing. However, we got enough data here that we could actually do our job. So here we have our points superimposed on what was then the camera-based shape model. I think I've expanded the points a little bit so you can see them. But we use this data to assess the scale, and we found some minor scale errors with the shape model. And the importance is this shape model is actually being used to navigate the spacecraft. So it's not, at this point, not primarily a science issue, it is an operational issue. So the other exciting thing is OLA, for each pulse, there's some noise in the receiver, and you can get fake pulses. So you can put out 500,000 pulses, and you can still get some false returns that don't represent anything but noise in the instrument's receiver. So each of these little solid dots, black and red, represent where we got a false return. And if you see the red ones are very in close to Bennu, and they got my attention because they were in spots where we might have expected satellites, and there were more of them in close to Bennu than I thought were statistically expected. So I spent a lot of time looking for imagery to add some credence that these were not just noise, but these were actually small satellites or particles around Bennu. And unfortunately, we had no imagery that was pointed in the right direction at the right time. And so, this got a lot of excitement from the mission because, it's both cool scientifically and hugely important from an operational standpoint if you've got things orbiting this asteroid that you would like to orbit. But it was, we could never confirm it. So everyone kind of just thought I was thought I was a little bit crazy, and we left it to be for a little bit. And then, we said Bennu was supposed to be smooth, and Bennu wasn't. So, here's a picture of Bennu. Here's a example of a little article from Nature. Asteroids bumpiness threatens U.S. plan to return a sample to Earth. This was no joke, right? There was no 25-meter smooth spots on this asteroid. In fact, we were struggling to find 5-meter smooth spots. So we drastically changed our plan and what instruments we were going to use to get to the surface of the asteroid. There was a huge amount of more work, and given the, you'll see some of the data from OLA that came out later, how important it is to understand the smoothness of the sampling sites on the asteroid. OLA really increased in its importance, and we actually had a lot more work to do, not just from a science perspective, but also to support the operations of the spacecraft. So here's where we really got our relief. So I told you just a few points as in preliminary survey, and we were kind of wondering what was going on, but we got a little closer. Now we're talking about 5 kilometers, and I was able to put together our first model of Bennu. So this is going to look like, not a very high resolution model compared to what I'm going to show you later, but this is still state of the art for any kind of asteroid mission. So, this would have been a very successful instrument with only a model, that had this level of detail. We actually used this data to really down select, to help down select sample sites because the topography at that scale was still better than other methods we had of assessing the sample site. So this is one of those moments where you just kind of wipe the sweat from your brow and said it's going to be okay. Then we moved, well, we had some other operations in between where we were really looking for satellites, because in that time we did get some imagery, some camera pictures of things orbiting Bennu. So we went on a search, and we certainly did find some, and there's a publication in Science related to particles coming off Bennu that's quite interesting if you're interested. Okay, now we're moving to orbital phase B. I think I'm talking a little longer than we wanted, but sorry. So this was our time to shine. And so here we moved to we were about 700 meters and away from the asteroid. And on the top right here, we had one of these little 2-dimensional scans. So this was about 120 meters by 120 meters of the asteroid, 3.3 million measurements in a single scan, and they took 5.5 minutes to take it. You can see there the amount of detail is already amazing. You do this many, many times. We have more than 900 of them that globally cover the asteroid. And we find features in these that we can match with other features. And you can see these 4 colored scans that are moving, that are superimposed on each other. And if you do that and match up these features and place them on each other, and you do that globally over the whole asteroid, and then you balance out any uncertainties over all of those scans, you come up with a global model of the asteroid. So our first high resolution model, this is a comparison, excuse me, this is a comparison of the camera-based shape model and the OLA shape model. And where it's blue, OLA's smaller, and where it's red, OLA's bigger. So you can see we're a little bit small at the equator by a couple of meters, and a little bit tall at the poles by a couple of meters. And you know, there's a little bit of debate about who's right, but we actually did not match the shape from camera images very well. So it became apparent that we were wrong here, and we went on a long search to figure out why. So 2 real options, right? We could have had a change in the mirror calibration with launch and during cruise to Bennu, or we could have got the calibration wrong. So we spent really from September of 2019 to a couple of months before TAG sorting all this out, and we're actually still building our final models. It turns out we have probably a little bit of both. We have an unexplained change that we don't quite understand in one of the axes of our mirror. And then because we did change our operational plan for orbital phase B a little bit because of spacecraft uncertainties being greater than planned, we scanned our mirror wider than we'd planned. And I think our calibrations in the corners, just because of some limitations in our test facility, not because anyone did anything wrong, was not as good. So we've actually used the data from the mission itself and the fact that we have all of these overlapping scans to come up with a better mirror calibration. So what you're seeing here is our shape model of OLA, of Bennu from the LiDAR. And this is what I'm showing you here is rendered from a 20 centimeter model. I've built once, and I'll build probably a little better one, 5 centimeter resolution over the whole asteroid. This is just unprecedented in any way, shape, or form. We have a lot more detail here. You can see, if I zoomed in, you could see little cracks and fissures and intrusions into rocks. You can see thermal fracturing, you can see layering. So there's enough work here to keep a whole team of geologists busy for a very, very long time. So we're really proud of it. In terms of, this is that same model, although it's a little bit smooth just to make the rendering go faster. This, I think, is a 40 centimeter model. And if you compare it to an image here, you can see that it really does a good job. The image has the advantage of having some albedo with it, some grayscale, whereas this is just a shape. So we don't see the some of our rocks here on the image are lighter in color, and we don't see that light in color, but in terms of the shape, now we have our model right. Here's a little more direct comparison. So we've been doing, finally, after spending a lot of time sorting out TAG sites, we've been doing some science, and one of the science questions, seems I've got some transitions, which I usually take out in this presentation. We have been looking at the shape of Bennu and what makes the shape, and we can talk a little bit maybe in the question period, but the southern hemisphere is a little bit rounder than the northern hemisphere. That has implications for both how Bennu was formed and how Bennu evolved. So it's actually a little bit interesting. So we looked at the basic shape, we looked at some of the finer scale morphology, here's some examples of some of the rock features that we looked at and how they form and what they can say about how the shape of Bennu evolved differently in the north and the southern hemispheres of Bennu. Gives you a little bit of an idea of how much detail we have. If you look at the scale here, this is a 2-meter bar, and you just see how much detail there is on these boulders. We have the sides of some of these boulders. And that was really a fortunate consequence of expanding the thing that causes problems about expanding the scan size from OLA, which caused all those calibration issues, or at least partly caused all those calibration issues, also meant that the geometries were such that we often captured the sides of boulders, and even in some cases the undercutting of boulders, and just have this wonderfully detailed model. You can see on the bottom left here where you can actually see layering on the sides of this boulder. Little bit on the very left side of this boulder, you can see a very smooth area, and that's where we don't have data, but those are the exceptions and not the rule for sure. So, you know, the consequences of the latest work we've done that was just published in Science was that we think that we have evidence for the first time of Bennu having undergone a spin up and then separated just a little bit. This is a very simplified picture, but as it spins up from this Yarkovsky related effect called YORP, so again, it's heating and cooling effect that's acting to accelerate the spin of the asteroid, it can partially come apart, and then like a figure skater, you know, that would slow it down because it's extending its arms, and then it would come back together. And we think we can see remnants of that in the shape of Bennu. So some of our co-authors had previously done computer models to show that this was a possible failure mode, but we think for the first time we actually have solid evidence from the shape that this kind of disruption can actually happen. So it's interesting. And here's our model with some superimposed camera and spectroscopy data on the cover of Science in November. So this is cool, Science, and being one of the most important journals. So we were pretty proud of this, and especially after having done so much work trying to make the model the right shape and to make all those 900 and some scans fit together properly. All right, just a few little slides on TAG. So this is what the TAG site looked like with OLA, and I should really know the exact dimension here, but I've forgotten the dimension. But you can see the TAG site is a smooth area which is in a crater, but there are still some significant rocks, and certainly this big rock on the at about the 10 o'clock on the crater, this big mound. That's been affectionately called Mount Doom because the spacecraft, we needed to keep it away from that. But this is all OLA data, so it gives you an idea of how important it was to have this data to assess the smoothness of the sampling site. This, I think, is a movie that's going to give you a little more picture. So this is shape superimposed with imagery, and it just gives you a sense of what we've been able to accomplish around Bennu that really is unprecedented from other missions. So far from a 25-meter diameter beach, but pretty much the smoothest we had. And again, it wasn't just the smoothest area we were looking for, but it was areas where we thought we could find these fine particulates that could be blown up into the sampling device. You can see Mount Doom there on the top left, but some other rocks were significant spacecraft hazards. Now, we had kind of a 5-meter uncertainty allowable here, and we would have been okay in most places in that 5 meters. I think the last I heard was the spacecraft team hit within something like 50, 70 centimeters from their targeted location. So they did really a fantastic job. they did a similar thing in the practice before, so you know, it wasn't a fluke. It seemed like they had this nailed down really, really nicely. That's what Bennu looks like close up. Trying to, I think this might be a different. All right, so here's a bit of a cartoony and a bit of real imagery of what TAG looked like. So the spacecraft had to actually match the rotation of the of Bennu, and then used features and camera images to try and locate itself relative to Bennu. This is real imagery now, coming down to touch Bennu, and that was our canister blowing and blowing material up into the sample collection. You can see that we did hit a spot that there was lots of loose material. Remembering that this is a lot of years of work for people. There was a lot of excited people watching that. There's Dante, who was the PI for the whole mission, thinking, oh, my life wasn't wasted after all. And there's a cartoon of us backing away. As many of you might know, there was a little bit of drama. We actually might have been too successful, and there were some little mylar flaps that should have closed, but we think we jammed this thing so full of material that it was starting to shed material in space. And if you remember from one of the earlier videos, there was supposed to be a mass measurement to make sure we got our 60 grams, which had to do with actually swinging that sampling device around in space to measure moments of inertia. It was decided that that would not be wise, given we were already shedding material through that nylon flap. And there was some visual work done where we could see, at least we estimated 400 grams of material with a 60 gram requirement. And there were many places where we could have material that we couldn't see. So the decision was made to stow, and everything's closed up now. And we'll be waiting for September of 2023 for that sample to come back. And I think we'll stop there while my voice is still with us a little bit.
Thank you very much, Mike. Yeah, take a break. And what I'm going to suggest is we take just a 5-minute break right now. I have 9:10 right now, so why don't we come back in 5 minutes for question and answer, and that'll give our guest speaker a chance to get a glass of water and rest his voice just a little bit. So we'll be back for Q&A in just a few minutes. In the meantime, if you've got some questions, please type them into the chat, and then we'll address those in a few minutes. Thanks a lot. You think you'll go back to part of your presentation, or do you want to unshare? There we go. Why can't I hear you?
because I don't know how to work a mute button.
This technology.
You'd think after spending many, many hours a day on Zoom, I'd have this down.
Yeah. Oh my God, the resolution of those shots was just amazing.
And I could, yeah, the challenge is with the data is so large, it's actually hard to work with.
Imagine.
So I would rather have just, you know, pulled it up and zoomed in and zoomed out. But even the 5 centimeter shape model I built last week had 1.5 billion faces in the model. And I actually don't have any tools that will display that all by itself. In order to look at it, I have to cut it up.
Yeah. Yeah, I'm not surprised.
And just dealing with all that data when we were trying to sort out our calibration issues has been, you know, it takes a lot longer than it would if we had, you know, a lot smaller data set. But we have 2.7 billion measurements during that orbital phase B. So.
Okay, the questions are coming in. So we'll give people one more minute to rejoin. Maybe I'll ask the first question. Just, you know, can you explain or describe the asteroid from a point of view that it's, you know, is it really just a rubble pile? And if you and I were there, we could just start picking up pieces and keep picking up pieces and throwing them off, and you know, there'd be no sort of hard, crunchy center or anything like that.
Well, you know, we don't know everything about the center. I mean, there's one of the papers in the Science Advances. So there were 3 recent papers in Science and 3 in Science Advances, which is a companion journal. So it looks at some inhomogeneity or models for inhomogeneity in the center that are compatible with the gravity model. So one of the big advantages of finding those particles is the particles and mapping their trajectories, which some of my colleagues were able to do, was a much better probe of the gravity field than the spacecraft was going to be itself. So they actually have much better gravity models of Bennu than we expected. But in terms of what's inside, we infer a little bit, but we do have very good volume measurements and we do have very good mass measurements. So, you know, we know that this thing is more than 50% void space, you know, either in large part in between things or voids that are inherent with the mineralogy itself. So it is really a rubble pile. You know, the other thing is one of the reasons why we got it wrong that Bennu wasn't a beach like we expected is because a lot of the large rocks appear to be quite porous. So, you know, if you think about how we determined it was a beach was, well, really how well the surface held heat is a measure, you know, of the density of the surface. So we did not see a very dense surface, and it was really compatible with fine particulates and not large boulders, but these boulders seem to be quite porous. If you look a little more carefully at that, at some of the tag imagery, like that movie I just showed, you can see that we actually pushed very, very deeply, like, you know, tens of centimeters into the surface of Bennu. So we are talking about something that's a loosely held together rubble pile with very little cohesion and a lot of porosity associated with it. Did that answer your question?
Yeah, no, that's great. You might have mentioned this before, but maybe could you give us a quick overview as to how it was determined before the mission that the asteroid was carbon rich?
That's the spectrum. So really those little squiggles in the spectrum. So if we went back and we looked at the taxonomy, there's the C class, which are the high in carbon. So you've got very low albedo, and then there's different classes of carbonaceous asteroids, and this is one of those subclasses. But it's ground-based measurements with telescopes. Primarily it's albedo, and then a little bit of the spectral signature.
Okay, great. Thanks for that.
So one other thing that people might not be aware of is that the high points of Bennu are the poles, and because Bennu spins, the equator, even though it's the furthest part from the center of the asteroid, is actually the low point. So all the material moves from the pole to the equator because the accelerations due to the spin and the acceleration due to gravity are the same order. So the low points are the equator and the high points are the pole.
So is there any mechanism, you know, whether gravitational or other, that would cause Bennu to become more spherical over time, or will it continue to look like it is, or maybe become more elongated?
Yeah, well, there's continued movement of material from the pole to the equator, and you know we have that equatorial bulge. I haven't actually paid too much attention recently, but the size of the equator is just about at its limit, because if material moves to the equator, you know, it can get thrown off. So there's some limiting geometrical factors, and the asteroid is accelerating its spin. So really, it's a question of how that acceleration interacts with the different internal strengths of the asteroid, and there's some debate a little bit on how the material moves, whether it's mostly superficial or whether there's some mechanism of moving within the asteroid itself. But it's not apt to get more spherical.
And do you remember what the gravitational force is compared to Earth?
Yeah,
Surface?
divide. It's a good weight loss program. Divide by something like 100,000. So if you want to lose weight quickly, just go to Bennu.
So it'd be one of those things where it'd be very difficult not to jump off the asteroid.
You could jump off, yeah.
Yeah, I mean, sometimes, yeah, I would imagine it might be, you could do it accidentally. Could you describe a little bit about the process of retrieving the sample then? Where is it going to end up?
So if you want to know, the best thing to do is go, I told you that the sample return capsule was Stardust Heritage, so you can actually go to the Stardust mission website probably and see some footage of their retrieval. But it ends up coming down in Utah in one of the, you know, the large UTTR, Utah Test and Tracking Range, something like that. So one of the big, you know, military cordoned off zones in the desert of Utah. So we're not going to land it on someone's head.
Yeah, some friends of mine actually went down and photographed the reentry, and just a spectacular sight. It's just an interesting question here, the excess of sample. Any concerns, you know, with reentry and recovery if you have the extra sample, or it's probably a small percentage of the weight of the whole reentry?
So it's a good question, actually, because that was one of the reasons why measuring the sample was important. This was so I was not directly involved in these discussions about, you know, whether we just stow and not do sample measurements, but as I understand it, it was determined that we would not be too far off if we just estimated that we had. So the max really is a couple of kilograms. So if we just assumed that we had a kilo in there, if we had 2, it would be okay, and if we had 0, it would be less okay from a science perspective, but we still wouldn't drop this thing on someone's head. So, so I think the assumption is that we're half full, and it'll be okay if we're all full or if we have much less than half.
Okay, let me look for another question here. A question about the organic molecules and just, I think, the measures that would be taken to prevent terrestrial contamination, and just how the sample will be handled once it's on the Earth.
Yeah, well, there was quite a bit of work done to make sure that the sample return capsule would be sealed up well. And all the materials that were used that could have contacted the sample were both, cleaned and measured very well, and so we know exactly what's there. There are also witness samples, so pieces of that same material that have been usually. So I'm not sure of the process completely because I wasn't involved. But usually, what you would do is you would take some of the same material and you would follow it along the whole process that those pieces of equipment would have gone through to get integrated onto the spacecraft, and then those would be saved so that if there was ever a question about contamination, you could go back and analyze those witness pieces to see if the contamination pre-existed or not. And then once this thing lands in Utah, you can imagine there would be a very quick, large number of people descend upon it to put it in some clean area until it could be taken to Johnson Space Center into those clean rooms. So.
Okay, and you were telling me earlier about the Canadian, what Canadian scientists like yourself will be receiving out of the sample, an estimate of, say, the number of grams you'll be receiving.
Yeah, so we had a pre-agreement with NASA that Canada would get 4% of the returned sample. So that doesn't sound like a lot when we were talking about 60 grams, but even 4% of 60 grams, you'd be amazed what could be done from a scientific perspective using modern instruments with very little bits of sample. If you go and look at what the Japanese are bringing back in Hayabusa 2, it's quite small samples, and they got a very small bit of sample done back in the first Hayabusa mission, and they did amazing science with just an unbelievably small sample. So it's quite a bit. And if we have 1 kilo or 2 kilo, then 4% is actually quite a bit of sample. So we're expecting quite a bit that we have to figure out how to keep pristine for current and future analyses.
Someone's asking about the rocks on Bennu. Is it possible that they're dust-covered ice chunks?
No, I think there's no evidence of that at all. So there appears to be some mechanism that makes the rocks porous, and I've been so focused on the shape model, I haven't paid too much attention to the current discussions on that. We were so focused on shape because the shape was driving the spacecraft to the surface in no small part. So I can't tell you what the latest hypotheses on that are, but definitely you could see that the tag head, the sampling device, penetrated into Bennu further than we thought it would. So I think we have some solid evidence that things are much more porous and friable than we would have expected, and we don't have a comet here.
I was wondering when you were mapping something like this, the first natural thing to do is to choose an equator, and of course the equator is pretty obvious on this. But did you have to choose like a prime meridian, sort of a starting place, just to sort of be your frame of reference? We
did. So yeah, so the pole you measure, and we refined the pole through the whole mission, so that gives you one axis. And actually we have even a minor update to the pole coming up, I think it makes a difference in the pole location at the pole of something like 5 centimeters. So I'm busy waiting, which is about 1 OLA spot. So it does make a little bit of difference to us. So I'm busy waiting for that latest pole. But we also, from the images, we selected a rock that had a feature, maybe a crack or like a V shape, and that was used as the prime meridian datum.
The people that control the rovers on Mars make it a point of naming every rock that looks interesting for their friend or their dog or whatever. Did that happen at all on some of these? I mean, somebody must have given that huge boulder in the southern hemisphere a name.
Yeah, Ben. So, yeah, I mean, you can imagine that rocks and craters at some point for a while, one of my colleagues named one after his dog and things like that. But I think and I'm not sure if it's all been approved yet, but the plan was, I think it has, the plan is mythical winged creatures. So, we have a griffin and we have a rock, ROC, and so it's all like that. And even you can see the winged creature in the sample site, which was called Nightingale. So.
Okay, question about asteroid mining. Did some companies are planning to mine asteroids? Did any people from those companies visit? What lessons might they learn from your mission?
This is not typically the kind of asteroid you would want to mine, unless you were trying to mine for any volatiles. So I'm not aware of any. I wasn't involved in any discussions with any asteroid mining companies with respect to this mission. I've interacted with them before in other contexts. But I think the primary things that we learned have to do with navigating around small bodies. The spacecraft navigation team they were just fantastic. So they over-delivered every time on their promises, and we, as I said, I think there's at least 2 Guinness Book of World Records that have to do with navigating around a small body. So.
Here's an interesting question. The studying of the asteroid, will it have any effect on its trajectory? That is the laser work or actually bumping into it?
Well, we're talking about such a small amount. So we touched it with, what amounted to probably 5 newtons of force for a few seconds. So if that caused us grief, then it's an unpredictable level of grief, and it's so small that I don't think we're in danger of having moved this asteroid into a collision course.
So obviously there will still be long-term plans to observe the asteroid from Earth over time, just to watch its trajectory and maybe even...
Well, as I said, we're developing models. There's a little bit of discussion going on about using this very high, so the model behind me, that's the OLA model, in case anyone has any doubt. But there's our current models, that relate to the Yarkovsky effect are not at the resolution of the model behind me, and there's some discussion about whether that adds value, or the limitations have to do with variations in the actual material properties, not variations in the shape of the asteroid. But we're discussing doing even more fine modeling, and so the better our models get, the more interest we'll have in actually tracking and trying to understand whether our models predicted reality as it moves forward.
Just a couple more questions here, Mike. One is about the inaccuracy in OLA with the calibration, and someone was asking if it would have made any difference if instead of a flat surface you used a rough wall or something to calibrate with, sort of more or less similar to the asteroid surface.
Yeah, no, I don't think so. There was either a mistake made, and we really don't think there was a mistake made. We went looking for one, and we couldn't come up with one that that mattered. So the changes we found were kind of two different areas. So, you know, we have two axes of the scanning mirror, azimuth, which is kind of the left, right, and then up and down we call elevation. So there was effectively no difference in the elevation calibration, and we found a 0.73%, 0.073% change in the, no, 0.73% change in the one axis. 0.07. Slipping digits here, it's getting late. So it's a fairly small change, and it was pretty much a linear change. And that's the one we can't explain, whether it was, you know, still an unexplained issue with the calibration or some change that happened in flight, you know, maybe due to launch, maybe due to some radiation effect that's stronger than we expected. We really don't know. We're currently still speculating. And then there was this issue about if you take the square and the corners were less well calibrated, and that I think is a limitation of the calibration setup, and the fact that we never expected to use the mirror out to those extents. But it turns out that, you know, both of those things we can actually calibrate better from the actual flight data than we could have ever done from the ground anyway. So we're quite comfortable with our current level of calibration now, and you can see that when you fit all these together, that, you know, you can look at the fine details of the rocks, and, you know, they all mesh together quite nicely. So I think, you know, it's caused us quite a bit of effort to get here, but, you know, the results are better than we would have done with even a better ground-based calibration than we have.
Okay, just to finish up, a question about Canada and space missions like this. When people hear about Canada participating in space missions, they might think that it involves writing a check. Can you say something about the training and career advancement associated with our participation? So I guess it's, you know, the expanding space technology and training people, say at Lassonde, and participating with other countries with missions like this. Can you talk a little bit about that experience?
Yeah, so as you know, this is my second go through these. I was also kind of started and led the engineering in that case, and not the science for the instruments that went to Mars on the Phoenix mission. So, you know, there's a variety of benefits for doing this. You know, as a university professor, I would say that one of the main reasons why we do these things is because it inspires young people to study science and technology. You know, so it's very difficult to put a value on that, but I think, you know, I get students that have watched the space program, and that's really driven them into science and technology fields, sometimes in space, and sometimes, you know, it's driven them, and their career trajectories have taken them to other places, like, you know, might be interesting to us now, like pharmaceuticals and things that are becoming a little more important of late. So that level of inspiration is really important. You know, these things do train people not just at universities, but also they tend to be some of the more challenging projects and the quicker turn projects in industry. So some of these long duration projects, like, you know, I've worked on a little bit the Dexter robots that are on the space station. Those are very long projects. The Human Spaceflight Program tends to have long duration. These things, you know, in a decade sounds like a long time, but they tend to be much shorter. You know, and remembering we launched, so we would have started the work in earnest in about, say, the beginning of 2011, and we launched in 2016. So from a development standpoint, this is very quick. So it keeps the people in industry sharp. And then I think, you know, it's important to spend some money in these areas, because, you know, as humans, we're really driven by curiosity, and it's important to not spend all our money on, you know, driving first order explanation, trying to learn things that we have never known before. But if we don't do any of it, I think we lose a little bit of what it is to be human.
Well, Mike, on behalf of everyone listening in, I'd like to thank you very much for your time and sharing with us this, this amazing journey that you've had over the last few years, and especially over the last few weeks. And it's really good of you to bring us into the experiences you've had and the successes. And just, I'm going to go back and look at that rotation video again, because that blew me away. I think it blew a lot of people away, and a lot of people a lot of people on the chat are thanking you for this talk.
You're welcome. So one thing you can do, by the way, is if you go to the Science Advances publications, which you can get from Science as well. So there's a series of 6 publications on Bennu, and one of them in Science Advances has my name as the lead author. You can go to the supplementary materials on that. It's all open source, so you don't need to have a subscription, and you can actually download that movie yourself. So you might find that interesting.
I think I might have it, and I think I might be able to put it in the chat. Is that the Hemispherical Differences paper?
Yeah, yeah.
Okay, I'll put it in the chat.
So I think the first movie is that exact video I showed you, or a version with the same shape model in any case.
Okay, here it is. Okay, great. Well, thanks very much, and I'm glad your voice survived. But I think we're going to call it a night. Let me just tell everyone a little bit more about our next meeting. In 2 weeks, we'll have a potpourri meeting. That's on December 11th, and we'll be talking about various short topics. And I think that's all we have. I mean, I'm just blown away by how great that talk was. So, Mike, again, thanks very much from everybody. And to all the participants here, please stay safe and well, we'll see you before Christmas, but take care. Thanks very much, everybody.
Thank you.
Mike.